Microclustering?
Sure. Microclustering, boy, there's a word for debate. There'll be arguments on both sides of it. When they talk about microclustering for water and breaking it down into smaller molecular sizes, it's more of a misnomer that explains a concept. If you think of low energy water as being clumped together like a bundle of grapes, kind of stuck together, if you think of iron filings, for instance, in an electromagnetic field, they bunch together. If these lose their charge, they kind of bunch together. The reason it becomes a problem is if your cells have what's called an aquaporin, which they do, it's really hard to jam all of these into that hole, or aquaporin, and so you get poor hydration. If you introduce an electric charge to this water, it kind of energizes the molecules, kind of like an electrostatic charge, and they start to separate a little bit. If you really zap the water, or really increase the charge on it, they disperse and they have a much bigger charge, at which point they can streamline much better. People talk about microclustering like it's molecular bonds holding water molecules together. A water molecule is that only. If you bond or create any other bonds of water molecules together, you get something altogether different. I mean, they show pictures like, 6 rings of molecules here, and they're all bound, and they've got hydrogens popping out. That's a whole different chemical compound. That's not water. Microclustering actually pertains more to what we would call the electrostatic charge on the water. The simplest example that makes sense is if you've ever seen a kid on a trampoline or playing with something, and there they are, they're all happy, but their hair is just all standing up on end, and each piece is spread out, separated away from the others. It's still chemically hair. We haven't changed the molecular structure of the hair. We haven't altered the human body anyway. There's simply an electrostatic charge that makes all the hair stand up. So that would be a lot of charge. And then if you had the same kid that had just started to jump and you only had a couple pieces sticking up, that's a light charge. And so it's more of an electrostatic charge on the membranes of the water, on the molecules, and the amount of energy that it has, that it allows it to separate out. This is simply too much of a clump or a cluster. If you were to think of those as a cluster of grapes, from a hydration standpoint, if that's a cluster of grapes and you're going to put them in a bottle, it doesn't take a rocket scientist to say, well, I'm going to take one grape off and dump it in and take another one and another one. That's kind of what it does. It's not exact science, but the concept of microclustering revolves around that issue. Each time the electron gets charged, there again, that's where your amperage becomes important, because 1 amp equals 6.24 times 10 to the 18 electrons. So the more amperage you have, the more energy or the more electrons you're dumping into the system. And when these things break apart, you actually get hydrogen and a hydroxyl. When you break 2 of them apart, you get 2 hydroxyls with a free electron. These become the dissolved hydrogen in water, and your body actually uses hydrogen gas as an energy source to fuel many of its cellular functions. If you look up cellular membrane, things like that, there's even pictures on Wikipedia, whatever, and it shows a cell membrane, and it's got the hydrogens here stuck in it, which, interestingly enough, the charged protons, by definition, won't cross through the aquaporin. They'll hang up in the cell membrane.